In this week's lab, we're going to investigate the extent to which glaciers are good indicators of climate change. The calculation of glacier mass balance allows us to quantify how a glacier is reacting to climate change, a change in temperature, change in precipitation, or both. Now, glacier mass balance is simply the difference between accumulation and ablation. Well, accumulation refers to those processes that add mass to the glacier. This is money coming into your checking account, snow coming into the glacier, either by direct precipitation or snow avalanching off adjacent mountainsides, adding mass, increasing the balance of that glacier. We have snow coming in. We also have snow coming out. Snow going out. Processes by which mass is removed from the glacier are called ablation. That consists of melting in the summer, and if the glacier terminates in a body of water, like a lake or the ocean, the glacier may also lose mass through the calving or breaking off of icebergs. For that reason, glaciers that end in water, tidewater glaciers, have the capability to retreat much more quickly than glaciers that terminate on land, because they have this additional mechanism, calving of icebergs, by which to lose mass. Now, if a glacier has a positive mass balance, that means there's more accumulation than ablation. In other words, the glacier is gaining mass over a larger fraction of its surface area. The glacier is going to react to a series of years or decades of positive mass balance by getting larger. The glacier will either get longer, or it will also thicken vertically. In other words, the glacier advances in response to years with a positive mass balance. The reverse is true when the glacier has a negative mass balance. When mass balance is negative, this means that accumulation is less than ablation. Glacier is losing more mass than it gains. It's losing mass over a greater fraction of its surface area. A glacier is going to react to years or decades of negative mass balance by shortening, retreating, and also thinning vertically. Measuring mass balance is technically simple. The equipment used is relatively straightforward, but it takes a lot of field and grunt work to accomplish these measurements, and it takes dedication to collect those measurements over many years to produce a record of mass balance that might reflect a change in climate. Again, change in climate is not measured day to day or year to year, but measured over longer time periods, decades to centuries. So to get a record of glacier mass balance that might be reflecting changes in climate, we need to be measuring mass balance for a given glacier over a period of at least several decades. To measure the accumulation, we'll simply want to visit the glacier at the end of the winter, end of winter or early spring, say April or May, and measure how much snow accumulated on that glacier during the previous winter. At the same time, we're going to set stakes in the glacier surface and note the position of the previous summer ice on that stake. We're then going to revisit the stakes at the end of the summer to see how much mass was lost at a given location. Assuming this guy is about 6 feet tall, his hand is holding the stake where the previous summer surface was. This glacier lost about 2 meters of thickness at that location over that particular year. In other words, it had a negative mass balance of about 2 meters for that location for that year. You would need to make accumulation and ablation measurements over as many different locations on the glacier as possible in order to calculate an overall mass balance for the total glacier surface. In thinking about how a glacier reacts to mass balance, we need to think about, or it helps to think of glaciers like a conveyor belt. Of course, a glacier is continuously moving. What it's doing is it's taking extra mass from up higher where it accumulates and moves that mass down lower to lower elevations, warmer temperatures, where that excess mass can be lost. In other words, a glacier is like a conveyor that moves snow and ice from the accumulation area where mass is gained to the ablation area where there's a net loss of mass from that glacier. So every glacier has an accumulation area and an ablation area. Accumulation area, we have net gain of mass. More snow falls over this part of the glacier in winter than can be melted during the summer. Then each glacier also has an ablation area, where there's a net loss of mass from that part of the glacier. And in acting like a conveyor belt, our glacier is going to move extra mass from the accumulation area, move it down slope to where it can be lost in the ablation area. The boundary between the accumulation and the ablation area is called the equilibrium line. When a glacier has an overall positive mass balance, that means it gains mass over a greater fraction of its area. When a glacier has an overall net negative mass balance, that means it lost mass over a greater fraction of its area. In other words, when mass balance is positive, the equilibrium line goes down. The boundary between the accumulation area and ablation area moves down the glacier. And when the glacier has an overall negative mass balance, the equilibrium line moves up the glacier, reflecting a larger ablation area and a smaller accumulation area. For a glacier to be in a steady state, in other words, to be in an equilibrium condition with the climate condition that glacier is subjected to, it would need to have about 2/3 of its area in the accumulation zone and about 1/3 in the ablation zone. As a general rule of thumb, this would vary for individual glaciers because each glacier has a different size and shape, but a good general rule is that a glacier that is stable has approximately 2/3 of its surface in the accumulation area, a net gain of mass, and 1/3 of its surface in the net ablation area, a net loss of mass. These photographs show Grinnell Glacier, which is in Montana's Glacier National Park. We can see that this glacier is not in equilibrium with the current climate. It has a large ablation area, as shown by the dirty ice. This is older ice exposed by melting during the summer, area with a net loss of mass. In contrast, its accumulation area is relatively small. This is the area that still appears white or clean because it's covered with snow from the previous winter that has not melted. This is the area with a net gain of mass. Does this glacier look like it has 2/3 of its area in the accumulation zone? Well, clearly it does not. Its accumulation zone is actually smaller than the ablation zone, more like 1/4 to 1/3. Better illustrated by looking at the photograph on the right, which is an aerial image of this same glacier. The area in yellow which I'm outlining now, shows the size of the glacier in 1993 when this picture was taken. The accumulation area in 1993 is this area that looks white or clean because it's still covered with the previous winter's snowfall. The remainder of the glacier surface, part of it is in sun, part of it's in shadow, is the ablation area. What would you estimate is the approximate fraction of this glacier surface area that is in the accumulation zone in 1993? Is it 2/3? Well, clearly not. A half? No, not that much either. It's more like 1/3 or even 1/4, telling us that this glacier is not stable. The glacier is going to retreat if the 1993 climate continues. The glacier over time is going to retreat to approximately this position, which would result in 2/3 accumulation area, 1/3 ablation area, which would make the glacier stable or in equilibrium with the current climate conditions. Now, glaciers have a lag or response time to adjust or react to a change in the climate. The larger the glacier is, the longer its response time. This glacier is relatively small, so it's going to react relatively quickly to changes in climate. But it's still going to take the glacier years to decades to react to a change in climate. By that time, the climate will have changed again. So the glacier is never really in equilibrium with the climate because it takes time to adjust. It takes the glacier more time to adjust to the climate than it does for the climate to change. Large ice sheets like Antarctica are so huge they take thousands of years to react to climate change. In other words, the ice sheets of Antarctica are still reacting to the climate change that ended during the end of the last ice age, 11,500 years ago. Now, the mass balance for a given glacier will change from year to year depending on what the climate was like in that particular year. This is illustrated by comparing 2 years of mass balance measurements for South Cascade Glacier. South Cascade Glacier is in Washington State, near the small town of Rockport, just south of Washington Highway 20. On the left, we see a negative mass balance here. We can see that the glacier had a net loss of mass over a greater fraction of its surface area. This would be produced by a year with relatively little snowfall, or say warm temperatures in winter, which allowed most of the precipitation to fall as rain rather than snow and not contribute to accumulation. Or it might be produced by an exceptionally long and hot summer, producing a longer period of ablation. In reality, probably some combination of the two. A winter with relatively little snowfall, followed by a long and warm summer, resulting in net loss of mass over a greater fraction of the glacier's surface. Now, using that 2/3 accumulation to 1/3 ablation rule, for the glacier to be stable, the equilibrium line would need to be approximately there, producing 2/3 of the glacier surface in accumulation zone, 1/3 of the glacier surface in the ablation zone. Well, for this particular year, the glacier has an overall net negative balance. We have more like 4/5 of the glacier in the ablation zone and only about 1/5 of the glacier in the accumulation zone. If these conditions were to persist for multiple years, the glacier is going to retreat to approximately that position, which would again produce 2/3 accumulation, 1/3 of the glacier surface in the ablation zone. On the right, we see mass balance measurements for a net positive year. The glacier experienced accumulation over a greater fraction of its area. This particular year, the glacier has approximately 3/4 of its area with net positive balance, and only about a quarter of the glacier surface area is in the ablation zone for that particular year. This would be caused by an unusually snowy winter, followed by a cool summer, increasing accumulation and decreasing ablation, causing the glacier to gain mass over a greater fraction of its area. Again, if these conditions were to persist, the glacier is going to advance or lengthen until it has about 2/3 of its area in the accumulation zone and 1/3 of its area in the ablation zone. The mass balance of South Cascade Glacier has been measured for about 50 years. During that time, the glacier has had mostly negative mass balance. And we know this because the glacier has gotten smaller with time, as shown by these photographs. Photographs taken about 70 years apart. We can see that during this time period, the glacier experienced predominantly negative mass balance. Why? The glacier is a lot smaller now than it was 70 years ago. That doesn't mean every year was negative. It's just that most of the years, more years than not, had a negative mass balance, causing the glacier to retreat during this time period. How does that compare to earlier time periods? Well, what I've drawn on here in blue is the position of the glacier in approximately 1880, as shown by the location of its moraines that it deposited during a period of cool climate conditions called the Little Ice Age. This is when glaciers advanced throughout the mountains of the Northern Hemisphere, starting around the year 12 to 1400 AD and reaching a maximum size in the mid to late 19th century. Since that time, climate has warmed. Some of that warming has been natural. Some of that has been in response to higher greenhouse gases due to fossil fuel use. But because the climate has warmed, we see that the glacier has experienced overall net negative balance and has retreated some distance away from its Little Ice Age moraines reached during the cooler climate period of the 19th century. The United States Geological Survey has been measuring mass balance on 3 glaciers, starting in the 1950s for South Cascade Glacier in Washington, and starting in the 1960s for Gulkana and Wolverine glaciers in Alaska. These 3 glaciers were chosen because they have relatively simple shapes, making it relatively easy to calculate the mass balance across the total glacier surface, and because these glaciers are relatively easy to access. And they also each represent a different climate zone or climate region. South Cascade Glacier represents the wet but relatively mild climate of the Cascades. Wolverine Glacier represents the wet but cooler climate of coastal Alaska. And Gulkana Glacier represents the cold and dry climate of the Alaskan interior. In your lab, you're going to be working with mass balance records from South Cascade Glacier, looking at how the mass balance has changed since those measurements began in the 1950s, and how those changes in mass balance show up as changes in the glacier size and the extent to which the glacier mass balance changes reflect changes in the global climate. As an example, let's work with the mass balance record from Wolverine Glacier. This is what the annual mass balance record looks like for Wolverine Glacier. We see years with positive mass balance, years with negative mass balance, as well as years that are neutral or closer to 0. What are the trends in this data set? In other words, we don't want to just list all the years with positive mass balance or list all the years with negative mass balance, but rather describe the periods of time when mass balance was mostly negative or mostly positive. Well, up until about 1976, the glacier had mostly negative mass balance. In other words, most of the years had a negative mass balance, with a few exceptions. The notable exception being 1970 that had a strong positive mass balance. But most of the remaining years prior to 1976, the glacier had mostly negative mass balance. Then we enter a period of time from 1976 until 1988 where the glacier had mostly positive mass balance. We see several years with strongly positive mass balance, some years that were close to zero, and just a single year with a strong negative mass balance. So overall, during this time period, the glacier had a mostly positive mass balance, whereas prior to 1976, it had mostly negative mass balance. Again, that doesn't mean all the years were negative during this time period, or all the years were positive during this time period, but rather that most of the years were positive between 1976 and 1988, and most of the years were negative between 1966 and 1975. Then after 1988, mass balance record changes again. Now the glacier once again has become mostly negative mass balance from about 1988 to present. Mass balance measurements continue for Volcanic Glacier, but they haven't been published since, or updated since 2004. If you want the more recent data, you could probably email the USGS and obtain mass balance measurements up till about 2012. Between 1988 and present, again, we see the glacier has mostly negative mass balance. Even the years that are positive are only slightly positive, and certainly not enough to offset these strongly negative mass balance years. This graph shows the cumulative mass balance over this time period. This is a running total of the observed annual mass balances. Remember, we said that up until about 1976, annual mass balance was mostly negative. That shows up as a negative trend in the cumulative mass balance until 1976. Then the glacier enters a period of time when its mass balance was mostly positive. That shows up as an increase in cumulative mass balance. In other words, the glacier is thickening over the time period 1976 to 1988, because most of those years have a positive mass balance. Prior to 1976, most years were negative. The glacier lost about 7 meters of thickness. It then regained that thickness during the period of mostly positive mass balance from 1976 to 1988. Then after 1988, the glacier's mass balance becomes strongly negative. Most of the years have a negative mass balance. There's only a few positive years, positive mass balance years, and even then, those years are just barely above zero. So we see the glaciers overall losing mass from 1988 to present. In this case, present is 2004. And because of having mostly negative mass balance years during that time period, we see the glacier has lost about 15 meters of thickness over that time period. Glaciers elsewhere have been losing mass during recent decades as the climate warms. This photo shows the summit of Mount Kilimanjaro, which is in equatorial Africa. Unusual place to find glaciers, except that the summit of this large shield volcano reaches nearly 20,000 feet in altitude. So despite its equatorial location, the summit is tall enough for precipitation to fall as snow and to support glacier ice. At least it used to be tall enough for the summit to sustain glaciers. Those glaciers have been getting smaller, and they're getting smaller surprisingly fast. These pictures are satellite images taken just 7 years apart, 1993 and 2000. Notice how much larger of an area is covered by glacier ice in 1993 than was covered by glacier ice just 7 years later. In other words, Mount Kilimanjaro has experienced a rapid loss of ice during this time period. Well, we only have satellite measurements going back a few decades, but people visited Mount Kilimanjaro much earlier than that. This map shows the area covered by glacier ice in 1912 compared to the area covered by ice in 2003. Area covered by ice in 1912 is shown in the light blue shading. By 2003, quite a bit of surface area has been lost from these glaciers. They're now much smaller, as shown by the area mapped in dark blue. This graph shows changes in glacier ice cover measured in square kilometers on Mount Kilimanjaro over the last 100 years. You can see in the early 1900s, there's about 12.5 square kilometers of ice cover on Mount Kilimanjaro. By the early 2000s, there was only about 1.5 square kilometers of ice cover on Mount Kilimanjaro. We can fit a trend to this data, a trend line to this data, and use these observations to make a prediction of how long it would take for the remaining ice to disappear if this rate of ice loss continues. What I've done here is I've put a linear trend line to this data. This equation describes that trend line. Remember, a line has a form, equation for a line has the form y equals mx plus b. M is slope, b is the intercept with the y-axis. In this case, x is year, and y is area covered by ice in square kilometers. If the loss of ice continues at a constant linear rate, how long will it take? In what year will the glacier ice cover be zero on Mount Kilimanjaro? In other words, in what year will there be no ice left on Mount Kilimanjaro? Well, to find that, we take our equation, we let y, which is the area covered by ice, equal 0, and we're going to solve our equation for x. X is year. To do that, we're going to subtract 229.84 from both sides, divide by both sides by negative 0.114 to isolate x, and using our calculator, we find that x equals 2016. In other words, if the retreat of ice cover continues at a constant linear rate, in the year 2016 there will be no more ice on Mount Kilimanjaro. Of course, if the climate stops warming or cools, retreat will stop, glacier ice cover would last longer. If the rate of warming increases or accelerates, the glacier ice would disappear more quickly. In your lab, you'll do a similar calculation for South Cascade Glacier. You have volume measurements, which is going to be your y-axis. Over several years, year is of course going to be your x-axis. Make a graph of the data, insert a linear trend line, obtain an equation, solve that equation for x by letting y equals 0. Use those observations to predict when South Cascade Glacier will be gone. If you want, you could also play around with different kinds of trend lines. For example, the data may better fit an exponential function or a polynomial function. Excel allows you to insert trend lines of different types, not just linear trend lines. If you want, you can play around with different types of trend lines and see how that affects your results.